Hi, this is my second lecture on polynomial regression models, and here is the content of this module: polynomial models in one variable. And we already talked about orthogonal polynomials in the previous lecture. And today we will be talking about piecewise polynomial fitting, and we will also talk on polynomial models in two or more variables. Well, so polynomials are used in situation when the response variable is nonlinear. And in the previous class, we learned how to fit a kth degree polynomial, and also we have learned how to fit a kth degree polynomial using orthogonal polynomials technique. So, I will just recall those things quickly. For the detail, you have to see my previous lecture. So, this is what the kth order polynomial in one regressor variable x. The model is y equal to beta naught plus beta 1 x plus beta 2 x square plus beta k x to the power of k plus epsilon. And we have realized that instead of fitting this model, there are several advantages if we fit this model, where P 1 is a orthogonal polynomial of order 1, and similarly P k is a orthogonal polynomial of order k. And this can be considered as a multiple linear regression model with k regressors, and here you can see the x matrix, which is the coefficient matrix. And so, once you have the coefficient matrix, you can compute x prime x, and then you can estimate the regression coefficients like alpha j hat and alpha 0 hat. And then the residual sum of square is summation E I square, which can be written as in matrix form. This can be written as y minus y hat prime into y minus y hat, and finally, this is equal to SST, which is SS total minus alpha j hat sum over j equal to 1 to k into summation y I p j x I from 1 to n. Okay. So, this one is so SS residual equal to SST minus something. So, this one is SS regression, and so the regression sum of square is this quantity, and here the regression sum of square due to the jth term or due to alpha j, we say, is the jth term in this expression. So, also I mentioned that all sum of square for alpha 1, alpha 2, alpha k are orthogonal, and their value they do not change depend on the order of the polynomial. So, if you instead of kth order, if you make it say k plus 1th order polynomial now, then the SS regression due to alpha j say less than or equal to k does not change, even if you increase the order of the polynomial. And finally, we had this ANOVA table. So, this is the total variation and this part is basically SS regression. So, SS regression is can be split it into SS regression due to alpha 1, due to alpha 2 and due to alpha k. You can write down separately to check the significance of each coefficient, and here is the ANOVA table we talked about in the previous class. So, what I want today is that I want to give an example to explain this orthogonal polynomial fitting. So, here is the example. So, you have the x variable. So, this is the regressor year, and this is the response variable income per share in dollar. So, different year you have different income per share. Well, so the question is find. So, if you plot say if you prepare the scatter plot for this x and y, here you must have observed that all the xi's are equally spaced. Okay. So, instead of 1986, you can call it just 1, and then this one is 2, 3, 4, 5, 6, 7, 8. So, if you draw a scatter plot, you will see that the scatter plot indicates that the response variable is nonlinear. So, you have to go for polynomial fit. So, the question is fit a polynomial of suitable order that will provide a satisfactory approximation function for this data. Okay. So, we have total 8 observations. So, what we will do is that we will try to fit polynomial of degree 6 first. Why we are going for degree 6? Because okay, I will explain that later. If you go for polynomial of degree 7, then there will be nothing left for SS residual. I mean, all the variability will be explained by a 7 degree polynomial, because the number of observations is 8. So, consider this polynomial. This is of order 6, because it involves p 6 x, which is of order 6. Well, now to fit this model, what we have to do is that we have to compute p naught x, p 1 x, p 2 x, like p 6 x here. Well, we know that p naught x is equal to 1 for all x. So, here the x is basically 1986, starts from 1986, but I will just call them like so x is basically 1, 2, 3, 4, 5, 6, 7, 8, that is all. Now, p naught x is equal to 1 for all x, for all x I you can put I equal to 1 to 8. Now, p 1 x, which is orthogonal polynomial of order 1, if you can remember that p 1 x is equal to lambda 1 x I minus x bar by d. This is what the p 1 x is, and I explained this thing in the previous class also. So, here x bar, you can check that x bar is the average of these values, it is 4.5, and then if you compute for x 1, that is equal to 1. So, 1 minus 4.5 is minus 3.5, and here you can see the d is equal to big 1, because the space between two value is 1. So, for x equal to for x 1 it is minus 3.5, and lambda is a value is an integer chosen in such a way that this polynomial value become integer. Okay. So, here you have to choose lambda 1 is equal to 2. So, that minus 3.5 is equal to minus 7. Similarly, for x equal to 2, you will get minus 2.5 into 2, that is minus 5. Similarly, you will get all the values here, and look at p 2 x from my previous class, and you can get this table. In fact, in exam generally this table is provided. Okay. So, once you have this table, you can estimate the coefficients alpha hat, right. So, these are the estimates of alpha naught, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 and alpha 6 hat. Okay. Now, what we will do is that we will make ANOVA table for the given data. We have to compute SS regression for say alpha 1. So, this is the SS regression formula. So, SS regression for alpha 1 is equal to alpha 1 hat summation y I p 1 x I equal I is from 1 to 8. So, everything here, and then you can compute SS regression due to alpha 1, and all these things are tabulated here. So, the SS regression due to alpha 1 is 0.771, and similarly you can compute the SS regression for alpha 2, alpha 3, alpha 4, alpha 5 and alpha 6, and here is the total variation 0.821, and the residual is 0.003. So, I wanted to say here is that, well, let me before that let me test the significance of different coefficients. So, let me start with alpha 1 hat. So, what is whether alpha 1 hat is significant or not. So, the model is y equal to alpha naught hat. So, the fitted model is this alpha 1 hat p 1 x like alpha 6 hat p 6 x. So, this is the fitted model. Now, I am trying to test the significance of alpha 1 hat, whether alpha 1 hat is significant. If it is significant, then that should be present in the model. If it is not significant, then this term should not be there in the model. So, how do I test the significance of alpha 1 hat? This is nothing but SS regression due to alpha 1 hat, that is 0.771 by MS residual. So, SS residual is same as MS residual, because the degree of freedom is. So, MS residual is also 0.003, because MS residual is equal to SS residual by the degree of freedom. So, this follows F distribution. So, this value is 257, and this is the observed value for alpha 1, and the tabulated value is the value you will get from the F table, and this follows this has the degree of freedom 1. So, F 0.0511 you can see from the table that it is 161.4, and so the observed value is greater than the tabulated value. So, alpha 1 is significant. So, alpha 1 p 1 x should be there in the model. Now, you see the SS regression due to alpha 2 hat is significantly smaller than the SS regression due to alpha 1 hat. So, what is this SS regression due to alpha 2 hat is the part of variability in y, which is explained by the by alpha 2 hat or the second order term. So, this is the part, this is the variability out of this variability, which is explained by the second order term, that is alpha 2 hat p 2 x, and these are quite smaller than the SS regression due to alpha 1 hat. So, instead of checking all this, I will see which one is the bigger one. So, for alpha 4 hat it is significant, I mean this is larger than the other alpha j's. So, I will test the significance of alpha 4 hat first. So, that can be tested. So, what I am testing is that I am testing this hypothesis H naught, that alpha 4 equal to 0 against the alternative hypothesis H 1, that alpha 4 is not equal to 0. So, to test this hypothesis, I will use this F statistic. So, F is SS regression or MS regression, basically this is 0.028 by MS residual, which is 9.3, and this F follows, F has degree of freedom 1. So, the tabulated value from the table is 161.4, and this one is much smaller than the tabulated value. So, alpha 4 is not significant. Since alpha 4 is not significant, you can easily test that, you can easily prove that the other alpha i's like alpha 2, alpha 3, alpha 4, alpha 5 and alpha 6, they are not significant. Okay. Not significant means you accept the null hypothesis that alpha 4 is equal to 0. So, you can put alpha 4 equal to 0 in the model. Well, so this all this test, what it implies that instead of going for a 6 polynomial of order 6, you can simply fit a straight line model like y hat is equal to alpha naught hat p 1 x. Sorry, alpha naught hat plus p 1 x alpha 2 hat. Okay. So, this is the model you can go for. Yeah. So, the straight line model is this one, and here is the fitted model you can see. And now, to double check whether this fit is good or not, you can compute R square parameter, coefficient of determination. So, here this one is nothing but SS regression by SS total. Okay. So, this is the SS regression and SS total. So, this R square parameter, it computes the proportion of variability in the response variable, which is explained by the model, the part of the variability which is explained by the model. And here you can see that R square is 94%. That means 94% of the total variability is explained by the model. So, which is quite good. So, finally, what we did here in this particular example is that we started with a 6 degree or a polynomial of order 6, and we have fitted that model using orthogonal polynomials, and then we have tested the significance of the higher order coefficients like alpha 6, alpha 5, alpha 4, alpha 3 and alpha 2, none of them are significant. So, we can remove them from the model and we can only continue with alpha naught and alpha 1, because alpha 1 is significant. Okay. So, finally, the conclusion is that instead of going for a higher order model for this particular data, we can go for a simple state line fit. Okay. And that is all for the polynomial regression model. Now, we will go for piecewise polynomial fitting. Okay, let me just explain what is this piecewise polynomial, why we need piecewise polynomial fitting. So, you are given a set of data x I, y I for I equal to 1 to n. You prepare the scatter plot. The scatter plot indicates that the response variable is nonlinear. So, you go for polynomial fitting, and we always try to keep the order of the polynomial low. So, if you see that low degree polynomial does not provide good fit to the data, what you will do is that you increase the order of the polynomial and see whether the higher order polynomial improved the fitting or not. So, if you see that the lower degree polynomial does not provide good fit to the data, and increase in the order of the polynomial also does not improve the situation substantially, then this sort of things indicates that the original response variable that behaves differently in different segments of the range of x. Okay. So, maybe up to certain range the response variable is some degree polynomial, and in the next segment it behavior change. Maybe in the next segment it is just a straight line, and in the next segment it might be quadratic, something like that. So, in those situations we need to go for a piecewise polynomial fitting, and I will be talking about this piecewise polynomial fitting now in detail. So, as I told that, so this problem means lower order polynomial provides poor fitting, but increase the order of the polynomial does not improve the situation. So, this problem may occur when the function behave differently in different parts of the range of x. Okay. So, the spline, now I will introduce some technical terms. This is also called the spline. Okay. So, the splines are piecewise polynomial of order k. Okay. And the joint points of the pieces are called knots. Okay. So, here specifically we will be talking about spline or no, we will be talking about cubic spline. The cubic spline that is for you consider the degree of the polynomial k or the order of the polynomial k is equal to 3 is usually adequate for most practical problems. Okay, so, here we will be talking about only cubic spline. Let me give the model for cubic spline in detail. So, cubic spline, a cubic spline with h knots, and the knots are say T 1 which is less than equal to less than T 2 less than T h with continuous first and second derivative can be written as so this is the response variable y which is a function of x. So, I am writing the cubic spline model for involving k knots. Okay. So, this is the model beta naught j x to the power of j is from 0 to 3 because of the fact that it is of order 3. It is a cubic spline plus beta I x minus t I to the power of 3 plus I equal to 1 to h. Do not worry, I will explain all this thing right now and also using I will illustrate this thing using an example also. So, what is this function x minus t I plus this is the notation which stands for this function is equal to x minus t I if x is greater than t I. That means, if x minus t I is greater than 0, then this one is x minus t I, and 0 if x minus t I, let me write in this way, less than equal to 0. So, this is greater than 0, this is less than 0. Okay. So, let me explain this model, and this might not be you might not be so comfortable with this model at this moment maybe. Let me explain this model for say 2 knots. Okay, so, this is my cubic spline model, and now I will consider a more specific case, say cubic spline, and here let h is equal to 2. So, there are 2 knots, that means 3 segments. So, we are considering a special case of 2 knots, and the knots T 1 and T 2 are known, we are assuming that. So, my model is y equal to beta naught naught beta naught 1 x plus beta naught 2 x square plus beta naught 3 x cube plus beta 1 x minus t 1 to the power of 3 plus beta 2 x minus t 2 to the power of 3 plus epsilon. So, this is the model we have to fit, and what does this mean? Now, if I use the meaning of this function, like then this is nothing but y equal to beta naught naught plus beta naught 1 x plus beta naught 2 x square plus beta naught 3 x cube. So, y is this plus epsilon in the range. So, I am dividing the whole range. Suppose the range of x is from a to b, this is a, b, this is the range of x, and I have 2 knots, so T 1 and T 2. Now, you can check that this y is equal to this in the range a less than equal to x less than equal to T 1, because here in this range x is less than T 1. So, this is equal to 0 and this is also equal to 0, because T 1 is smaller than T 2, and y is equal to beta naught plus beta naught 1 x plus beta naught 2 x square plus beta naught 3 x cube plus beta 1 x minus T 1 to the power of 3. This is my y, or this is my model in the range x greater than T 1, but less than equal to T 2. I am sure if you just put the meaning of what this function stands for, then you will get all these things. And then the last one is beta naught naught plus beta naught 1 x plus beta naught 2 x square plus beta naught 3 x cube plus beta 1 x minus T 1 to the power of 3 plus beta 2 x minus T 2 to the power of 3 in the range x greater than T 2, but less than equal to b, because in this range when x is greater than T 2, x minus T 2 plus is equal to x minus T 2. So, you can put that here, and here also when x is greater than T 2, then it is also greater than T 1. So, x minus T 1 plus is nothing but x minus T 1. So, it is a simple verification. So, this is the model for cubic spline involving only 2 nodes, and here we wrote it for general case. Now, the problem is deciding the number of knots and the position of the knots. Okay. So, deciding on the number and positions of the knots and the order of the polynomial in each segment is not a simple job. Okay. So, according to Auld 1974, what he suggests is that as few as knots possible. So, as few knots as possible with at least 4 or 5 data points per segment. Okay, so, we understood the cubic spline, which is a particular case when the order of the polynomial is 3, and also for we explained this case for we explained this cubic spline involving 2 knots. Okay. Now, we should be able to, we should be given a model like this say with involving 2 knots, we should be able to fit the regression coefficient, because this one is nothing but a multiple linear regression model. Okay. And so, we should be able to estimate the regression coefficients. Let me talk about that little bit. What is the X matrix and all these things. Okay. So, the model is y equal to beta naught naught plus beta naught 1 x plus beta naught 2 x square plus beta naught 3 x cube plus beta 1 x minus t 1 to the power of 3 plus beta 2 x minus t 2 to the power of 3 plus epsilon. So, this is the cubic spline model with 2 knots, that is h equal to 2. So, I just want to mention how to estimate the regression coefficients. So, first you try to compute the coefficient matrix X, which is nothing but 1, I mean 1, and then you write down the column corresponds to the response corresponds to the regressor x, and then x square, x cube, and then x minus t 1 to the power of 3 plus x minus t 2 to the power of 3 plus. So, here is the X matrix. If you do not understand, again I am going to give an example to explain all these things, but yeah. So, if you have this coefficient matrix, so this is the coefficient matrix, and then you can write this cubic spline model with 2 knots in terms of matrix notation as y equal to x beta plus epsilon. and then you know what is beta hat. Beta hat is equal to x prime x inverse x prime y, and of course, the beta here is beta naught naught, beta naught 1, beta naught 2, beta naught 3, beta 1 and beta 2. Okay. So, there are 6 regression coefficients to be estimated, and here is the ANOVA table for this. Source, degree of freedom, SS, MS and the F statistics. Okay. The source is the variation SS regression, and then residual, and here you have the total. Okay. And if you have n observations, then the degree of freedom for total variation is SS total is n minus 1, and here you can see that there are 6 parameters to be estimated. So, when you compute the degree of freedom for residual, this E I, there are n residuals, and since you have 6 parameters, there will be 6 restriction on E I. So, the degree of freedom, residual degree of freedom is n minus 6, right, n minus 6. So, the regression degree of freedom is then 5, and so this is SS regression, SS residual, SST, and once you divide this by 5, you will get MS regression, MS residual, all these things, and here is the F statistics, which is MS regression by MS residual. So, this is a global test, whether the model is significant or not, and if you want to test a particular parameter, whether this is significant or not, then you have to find the SS regression due to this parameter or this term, due to this term, and then you compute SS regression due to beta naught 3 by MS residual. So, you know all these techniques. Well, let me explain this cubic spline with 2 knots using an example. So, this is called voltage drop data, and here is the response variable, and you have one regressor, and there are total 41 observations. Okay. And I should mention that the source is from Introduction to Linear Regression Analysis book. And so, you have x I, y I. So, you have x I, you have observation x I and x I, y I for I equal to 1 to 41. So, the first step is that you prepare the scatter plot and see the behavior of the behavior of the response variable. So, here is the scatter plot for this data, and this scatter plot clearly indicate that the response is nonlinear. Okay. So, we can't go for simple linear regression model. Well, so what you can do, you can start with say if you want to start with a cubic polynomial first. So, you start with the cubic polynomial, you fit a cubic polynomial to this data. You know how to fit cubic polynomial, right? Either you can use, so you have to fit a model like, sorry, here it will be cube. So, you have to fit a model like y hat is equal to alpha naught plus alpha 1 x plus alpha 2 x square plus alpha 3 x cube plus epsilon. So, if you fit that model say using orthogonal polynomial, here is the fit, and now to check whether this cubic polynomial fit to the data is good or not, the standard technique is that you go for the residual plot. This is what the residual plot is. Residual plot. So, what you do is that you plot the residual E I against the estimated response. So, here is the residual plot, and I will talk about this residual plot later on. This is for the cubic spline model. So, the residual plot is not so good, because you can see the residuals are not centered about the line E equal to 0. So, that means this indicate that the cubic polynomial fit is not so good for the given data. And next what we will try is that we will go for the cubic spline model with two knots and two. So, the knots we will choose, like the first knot is T 1 is equal to 6 here, and the other knot we are going to choose is that T equal to 13. That if you want to say me why it is so, I can explain this T 2, because from T 2 onwards, like here you must have observed also that all these xi's are equally spaced, and here the d, the difference is 0.5. So, if you see from here from 13 onwards, the response variable start decreasing, and from here it is always increasing, but if you look if you have a look of the scatter plot, might be that indicates. So, 6.5 is somewhere here. So, you want to have a segment. So, this is one segment, this is one segment, this is my T 1, and then the 13 is 11 to 13. So, this is 13. So, this is T 2. So, I am taking this is as my one segment, and then T 1 to T 2 is my second segment, and then T 2 to up to 41 or whatever, up to 20, it is the third segment. And using T 1 is equal to 6 and T 2 equal to 13, we will fit a cubic spline model now. So, here is the model now. This is the model we are going to fit. You can see that T 1 is equal to 6.5, sorry, it is 6.5, and T 2 is 13. And what you have to here I will explain now how to get the coefficient matrix, because once you have the coefficient matrix, you can do all the calculations, you can estimate the parameters and all these things. So, you see here for the first segment, these are the x's value. So, first segment is from 1 to 6. So, from this is my first segment. So, from 0 to 6.5, you have you just you have the x values, you squared them, and here the cube, and this function is 0 for the first segment, and this function is also this function x minus 13 to the power of 3 plus this one is also 0 for the first segment, and for the second segment or in the second segment, we have these are the x values. So, you can square them and cube, and in the second segment this x minus 6.5 plus is equal to x minus 6.5. So, you can see accordingly I have tabulated the values here. So, x is equal to 7.0. So, 7.0 minus 6.5 to the power of 3, and in the second segment this quantity or this term is equal to 0, and here is my third segment. These are the x values, square, cube, and in the third segment this one is x minus 6.5 plus is equal to x minus 6.5, and similarly in the third segment, since t is greater than 13 here, starting from 13.5. So, x minus 13 plus is equal to x minus 13. So, you put the x values here and you get the coefficient matrix. So, I wanted to explain this coefficient matrix, and I hope that it is not so difficult to understand. And once you have the x matrix, you know we can write it in the matrix form, that y equal to x beta plus epsilon, and you can compute or you can estimate the regression coefficients beta as x prime x inverse x prime y. This is how you get all these estimates. Now, the job is we have the fitted model using cubic spline and two knots, one is 6.5 and the other one is 13. Now, to check whether this fit, whether the cubic spline is better than the cubic polynomial fit, we have to again go for the residual plot. So, here is the residual plot for the simple cubic polynomials, and here is the residual plot. This is again E I against y I hat. This is y I hat, this is also y I hat, estimated response. So, this is the residual plot for the cubic spline model, and here I believe that the residuals here are almost centered about the line E equal to, this is the line E equal to 0. So, this residual plot is better than the residual plot for the cubic polynomial fit. So, this indicates that that the data we have that behaves different in different segments. So, that is why cubic spline model provides better result than cubic polynomial fit. So, that is all for today, and today we explained we have illustrated polynomial regression, orthogonal polynomial using an example, and also we talked about piecewise polynomial fitting, and also you have given an example to illustrate cubic spline model involving two knots, and that is all for today. Thank you.